Hello everyone, and welcome back to Electronics Prepper, the channel where we try to learn as much as possible about electronics to become more self-reliant to technology and prepare for the future. In today's video, I want to discuss about the problem of measuring and monitoring DC currents through resistors, through shunt resistors. Something we may find we need to do in larger devices such as power sources, accumulator charges, or simply monitoring systems. I will go through each option that we have and see what are our advantages and disadvantages for each. In the next video I will post soon, I will show you where exactly I needed to use such a circuit in creating a simple accumulator charger that can be powered from an old computer power source directly from the 5-volt rail. The circuits I will show you today are pretty much universal. We will be able to use them both in linear power sources as well as switch mode. So, if you're interested in these topics, keep watching and stay tuned to this video. I will go through all of the details, but first, allow me to thank the sponsor of this video, which is PCBWay. PCBWay is a leading PCB manufacturer that can help you build your dream projects, no matter how advanced they are. They can create just the PCBs for you, and you will place components on them, or they can help you solder components through PCB assembly services, so you don't have the tedious work of doing that. If you're creating a full device, they can help you create a plastic case through either 3D printing or injection molding services, or even CNC machining if you need custom metal pieces for a metallic case. You're free to use your favorite design software, upload the Gerber files, and one of their professional representatives will contact you offering you one-on-one customer service. All you need to do is go to PCBWay.com, the link is in the description. Thank you PCBWay for sponsoring this video, and now let's get started with the topic of today's video, which is how to measure currents through a certain circuit. Why we might want to measure currents? Well, it's very easy, it's very simple. Sometimes we need to just know how many amps are flowing through a certain circuit. Some other times we don't just want to know, but we also want to control the output of, let's say, a power source, how much current goes into a load, and we will want to either limit that current or even just cut the power completely from the output if the current goes above a certain limit. For that, the simplest way of measuring is to use a shunt resistor. Basically, it's a very small value resistor that is placed in series with the load, and of course, according to Ohm's law, we will have a voltage drop on that shunt resistor that is dependent of the resistance herself, which is a constant. In our case, she will be a constant, and also the current that flows through that resistor, which will be, of course, variable and will be the one that we care about. Now, when it comes to shunt resistors, we basically have two options, and those options are dictated by the polarity on which we place that shunt resistor. We either have the option of placing that resistor on the positive side, also called the high side in English, or we can potentially place that shunt resistor on the negative side, also called the low side. Each options come with different advantages and disadvantages, so in the first half of this video I will discuss about what are those advantages and disadvantages, what needs to be done, what are the problems. In the second half of the video I will show you a circuit that I have tested recently. I have created and tested recently that allows us to use cheap, easily available comparators on the market to create a pretty good precision measuring circuit. Okay, so for now, for the first half of the video, let's go through what are our options. Like I said, a first option would be to put the shunt resistor on the positive side of the entire circuit. We will keep assuming that the negative polarity of our power source is the ground, okay, which in today's electronics it's pretty much always like that. I remember when I was a child and we still had some circuits made with germanium transistors. For some reason most of them were PNP, and because of that the designers favored placing the positive polarity to the ground and making that the ground, and everything else was negative relative to the ground. But I haven't seen that in quite a while, and I don't think it's a common practice anymore, so we can safely assume that the negative is the ground. Even though in my schematics I won't show you the ground symbol, we can just assume the negative is the ground, okay? So when we place the shunt resistor on the positive side, on one hand we have the situation with the minus of the source being the same as the minus of the load. Okay, I've placed a simple resistor here to signify the load, but of course the load is always something much more complex. The shunt resistor on the positive side tends to be an ideal combination, since we get to keep having the minus of the source common ground with the load, and this is something that we may want, or sometimes we may even need. This is the only possible option when we have multiple voltages with common minus ground, okay? So let's say that we have something like this. We have multiple voltages, but they are all referenced relative to one ground, one minus point. The simplest example would be a computer power supply, okay? We have a ground and then we have multiple voltages, 3.3, 5, 12 volts, even some negative ones relative to that ground, which is the minus polarity, okay? If we have different, and of course we will have different loads, different circuits, if we want to measure the current through each circuit independently, then we need to place the shunt resistor on the positive side, or on the high side, like sometimes it's referred to. Placing a shunt resistor on the minus will make it so that the current that we will sense will be the total current from all the power supplies through all the loads. So we won't be able to separate currents per load with a minus placed shunt resistor, okay? However, this option is more difficult to implement because it either needs a separate IC, separate chip. Most of the times, maybe not quite all of the times, but most of the times we will need a separate chip, to a separate op-amp or comparator to allow us to do some tricks to measure this current, or even a specialized integrated circuit such as ENA 180 or something like that. I can quickly show you, for example, this is a specialized circuit, and of course there are many others like this. I'm just showing you one model, which can be both used for the low side and high side current sense monitoring. But the advantage of such a chip is that, of course, we get maximum precision and quality and ease of implementation. However, because this chip is specialized, we need to buy him separately. It costs a bit more than, you know, a very cheap op-amp or comparator, and also we may want to have a relatively large quantity of these chips, which will not be only a financial problem but also a stock problem, because maybe we will find that there aren't enough chips on stock for us to just buy them. So for that reason, we may want to just have a solution that does not require a separate specialized chip, but allows us to just use an op-amp, a regular op-amp or comparator. However, in that case, we need to perform some tricks and we need to basically solve some problems. Therefore, this solution overall is more difficult to implement than when we have the shunt resistor on the negative side. Okay. And now let's talk about the shunt resistor on the negative side. It's easier to implement because, at least relative to the negative polarity of the source herself, which is in this case I've just placed the battery, you know, on my schematics, but it doesn't have to be a battery. We can have anything here, and we will typically have a power source. Relative to the negative pole, this shunt resistor will develop a positive voltage dependent on the current. So in a way, theoretically, it's easier for us to, you know, have this voltage directly influence the rest of the circuit. However, there are a few disadvantages. First of all, the load is no longer connected with the source directly, or at best, in case where we don't have, by the way, I forgot to mention, I've also placed this NPN transistor just for the sake of showing you that in most cases we will have a regulating device that will be either a bipolar transistor or a MOSFET transistor, and this one will also be placed in series with the load. It doesn't matter if the shunt resistor is placed on the positive side or on the negative side, we will most oftenly have this regulating device, this regulating component, which will be placed in series, and therefore we will also have a voltage drop on her. So you know, it's useful to see this in this schematic to better understand what's going on in the circuit. So in this case where the shunt resistor is placed on the negative rail, the load is no longer connected with the source directly, or best case scenario, in the rare cases when we don't need a regulation device, we can connect the load's positive pole to the source's positive pole, but the negative will no longer be connected because there will be the shunt resistor in between. This may be a problem or may not be a problem, depending on the case. If we have multiple voltages, like here, that are connected to a single point, which is the minus, the ground, at least as far as the power supply is connected, is concerned, then if we put a shunt resistor on the negative side, we will have to put one shunt resistor for each load, for basically each voltage, and this will make it so that the negative polarity of each load will be different. They will not share a same point, a same ground. Okay. Again, this may be a problem or may not be a problem depending on the case. But in general, we can consider that this cannot be used for multiple voltages with common ground, especially when we want the common ground to be, well, common to all the loads as well. Now, there are actually two different options when strictly speaking about this option of placing the shunt resistor on the negative side. There are actually two different sub-options, if I could call them like that, based on where exactly do we power the control circuitry. And depending on that, the voltage regulation for our load can be affected, because since the shunt resistor is in series with the load, the shunt resistor will constantly have a voltage drop, which will be dependent on the current. Of course, this is what we want, but the problem is in certain cases, the voltage on the load will not remain very constant, but will drop the more current will flow through the load because of this shunt resistor's drop. And because the controlling circuitry will not be able to know and compensate for this voltage drop. Okay, so sometimes this option can be problematic in the control circuitry for the output voltage. And now let's dive a little bit deeper into each of these options, high side and low side, and let me quickly present some circuits that can be used to you know, accomplish both tasks, but what are the problems and what are the limitations for each. So if we discuss again about the positive side or a high side shunt resistor, the fundamental problem that we have is that we have a voltage relative to the positive polarity of the power supply, and this is not really useful in the vast majority of cases, because our control circuitry will be referenced to the ground. So the voltage that depends on the current, we will want to be referenced to the ground, not to the positive side. The positive side will be useless for us. There are only a few cases when we might find that a certain integrated circuit that's very specialized for, let's say, switch mode power supplies actually measures the current from the high side, but this is because internally he has all sorts of specialized circuitry that you know, is able to work with positive referenced voltages. However, if we are to design our own circuits and use you know, simple components, use discrete components, even just op-amps can, or comparators can be seen as discrete, then we will need to have a ground referenced voltage. So we need to do a trick to basically take this high side voltage and mirror that to the low side somehow. And the easiest way is by using a comparator or an op-amp with 2 extra resistors and 1 transistor, which for he doesn't really matter if he's bipolar or MOSFET, at least from the point of view of him doing his job. However, we will pretty much always want to have a bipolar transistor because MOSFETs tend to need higher voltages to be turned on, and sometimes we may not have this voltage, okay? Especially if, let's say, our power supply is 5 volts or even lower, 3.3 volts. The voltage that is between the gate and the source of a MOSFET might just not be high enough in our circuit to, you know, allow us to open that and the entire circuit to work. So for the most part, we will think that we will need to use a bipolar transistor here. Okay, so how this circuit works, and by the way, this is taken from a common amplifier, LM358 datasheet, Texas Instrument datasheet, if I remember correctly. So this is not exactly my invention by any means. How this works is that we are setting this comparator to monitor essentially 2 voltages and make it so that I mean, by controlling his output, he makes it so that the voltage on one resistor is the same as the other. So we have on one hand the shunt resistor, and connected to the shunt resistor board on the input we have another resistor, okay, which is being turned on and off by this transistor, which in turn has yet another resistor down to the ground. And this op-amp or comparator, this monitors the voltage both after the shunt resistor and after this particular extra resistor on the high side. The idea is that he will make it so he will turn on and off this NPN transistor so that the voltage drop on this upper side resistor is the same as the voltage drop on the shunt resistor, which of course it's a measure of the current that flows through the load. Okay, because of that, of course, here we will have a current that flows through this side of the circuit, through this upper resistor, goes into the transistor, gets out through the emitter, and then flows through this other low side resistor. And this current will indirectly also be dependent on the current that flows through the load. So this way we can easily create a low side voltage that is directly dependent on the current. Okay, because let's say actually, let me just a moment, let me open the data sheet where I first saw this circuit, so that we can have some actual values to be able to do some calculations and you know, explain to you a little bit better what's going on. Okay, so this is the circuit. Okay, so in this example we have a 100 milliohm shunt resistor and then a 100 ohm resistor here on the high side and the 1 kilo ohm down to the ground. So let's say that we have 1 amp flowing through the load and obviously through the shunt resistor. 1 amp means 100 millivolts across the shunt resistor. This comparator will turn on and off this transistor such that on this 100 ohm resistor there will be also this 100 millivolt voltage. Okay, because that's what a comparator does. He does all his best to, when he has a feedback loop, okay, not in an open loop, but when he actually has a closed feedback loop, he makes it so that both inputs are at the same potential. It's true that it's the same potential relative to the ground, but it doesn't really matter because for all practical purposes it will be the same, since we have the same positive rail that is connected to both the shunt resistor and this 100 ohm resistor. Then, you know, a voltage relative to the ground is just the total voltage minus this upper side voltage, and vice versa. Okay, so if we have 100 millivolts, we have 1 amp through 100 milliohms of shunt resistor, therefore we have 100 millivolts of voltage. The op-amp will make it so that this 100 millivolts will be mirrored on this root 2 resistor here. 100 millivolts divided by 100 ohms is a 1 milliamp of current. But this 1 milliamp of current flows not only through root 2, but also through this NPN transistor and down to the ground through this root 3 resistor. And since this root 3 resistor has a resistance of 1 kilo ohm in this case, 1 milliamp flowing through 1 kilo ohm will generate a 1 volt voltage here, reference to the ground. So for each amp that will flow in our circuit through the load, we will have 1 volt relative to the ground. And this voltage can be further passed to the rest of the control circuitry, you know, which who can do the rest of the stuff that needs to be done in order to control. Perhaps we want a constant current source, so we can use this voltage, you know, to feed into the control circuitry, and the control will turn on and off the current through the load. Or maybe we just have we just want an overcurrent protection or whatever. Okay, this is the general principle of functioning of this circuit. It's pretty easy. However, there are a few problems. One of them is the fact that we either need a rail-to-rail op-amp, because the inputs need to go up to the positive rail, okay? Or we need to have an op-amp like TEL 060 something, 070 something, 080 something, which are not rail-to-rail, but their common mode input voltage range can go up to the positive side. Or if we choose, and this is something that sadly these guys from Texas Instruments did not mention here, if we choose a simple comparator or a simple op-amp that is not rail-to-rail by any means, then we need, when the inputs cannot go up to the positive rail, then we need to power this from a higher voltage. So we need to have an extra voltage here on top of this voltage from our main source just to power this op-amp or comparator, and sometimes we just don't have that. Okay, so that would be a first set of problems. The other set of problems is not quite so it's not quite so obvious, but you know, any op-amp and any comparator has a few characteristics that are problematic to us, and we consider them errors. And one of these errors are so let's say that we talk about very cheap and simple and easy to find on the market comparators such as LM339 or 393. Electrically speaking, they're the same. Well, all op-amps and all comparators have what's called input offset voltage, input offset current, and input bias current, among other things. Now, what we care about in this particular circuit is the input offset voltage. Depending on, because this voltage acts as an imbalance between the two inputs, and therefore the two inputs will not correctly measure the voltage drop on these high side resistors, which means that in turn they will make it so that the low side voltage will be a bit skewed. Okay, and to make matters worse, not only this offset voltage matters, but also how small the shunt resistor is. The smaller, then the bigger the problem. And also this error, this overall error that is introduced by the offset voltage manifests herself a lot more at lower currents rather than higher currents. So let's say that we want a shunt resistor of only 50 milliohms, okay? Like in my case, in the circuit that I will show you in the next video, I wanted to measure currents up to 10 amps, but I wanted to have as small voltage drop on the shunt resistor as possible. And I chose 50 milliohms. In this way, 10 amps will have only a half a volt voltage drop. The total error can be expressed as this offset voltage relative to the shunt resistor's voltage, which in turn is the product of the shunt resistance and the current that flows through that shunt resistor, which is the current that goes to the load. Okay, so if we are to calculate, let's say, you know, we are told in the data sheet that for an LM339 the typical offset is 2 millivolts, maximum 5, but can go up to 9 for full range temperature. So let's just take 5 millivolts, which is roughly the middle between 2 and 9 millivolts. Okay, so if we consider that we have a 5 millivolt offset voltage, a 50 milliohm shunt resistor, like I said, and we want to measure 10 amps, then at 10 amps the voltage that will be generated here on the low side, which is the voltage that we care about, will have a 1% error. Okay, because 100 multiplied by this voltage divided by 10 amps multiplied by 50 milliohms is 1%. However, and this 1%, you know, we might say, okay, it's not bad, it's acceptable. Yeah, however, as it may happen, we may want to, we will not always care about only high currents and not small currents at all. We may care about small currents as well. In my case, you know, I wanted to measure 10 amps maximum, but I wanted to have a resolution of a few hundred milliamps at worst, or a few tens of milliamps at best. So you know, I wanted this circuit to, or whatever circuit I would use, to be decent at measuring the current even at small values. And if we are to replace this 10 amps with only 1 amp and keep everything the same, because of course the offset voltage is constant, the shunt resistor is constant once we choose him, well, at 1 amp we see that we have a 10% error introduced in the entire circuit, okay? Because the upper side of the division remains the same, but on the lower side we have smaller currents, therefore the ratio is bigger, right? So at 1 amp we have 10% error, which is 10 times more than at 10 amps. And at 100 milliamps we will have a 100% error of the voltage that gets generated here and that we care about. So yeah, needless to say, this is a bit of a problem. So we have a few options, okay? Either we use a precision op-amp with an offset voltage that is below 1 millivolt, preferably well below 1 millivolt. Or we use a regular op-amp or comparator that has a null offset correction, or we perform externally this null offset correction somehow, okay? Because otherwise we won't be able to use this this solution, this high side measurement solution, okay? So we need to be aware of these errors because they are inherent to this topology. Like I said, sometimes we just need to have a high side current shunt, so we cannot go with other options that don't have this big problem. But you know, sometimes we can't. Now, if for some reason we cannot use an op-amp here that is either rail to rail, or the input voltages can go up to the positive rail, we can try to mitigate this problem by, instead of comparing these relatively high voltages that go outside of the input common mode range, we can divide these voltages through some voltage dividers, which again, in theory, if everything would be perfect, this would work without a problem. So like I said, instead of sensing the voltage here on this upper side resistor and on the shunt directly, we use two voltage dividers. Of course, we need to use the same ratio between these voltage dividers, and we can, you know, connect the op-amp or the comparator like so. And let's say we use the same value resistors, so basically this will halve the voltages, and for all practical purposes we will be within the input common mode range of whatever op-amp or comparator. However, now we have an even bigger problem, because this attenuation factor, right, because any voltage divider introduces an attenuation factor basically. This attenuation factor essentially becomes an amplification factor for this error that I've shown you earlier, okay? Because, you know, in order for there to be small differences on the input of the comparator, there need to be larger differences here on the upper side, because those larger differences get to be, you know, attenuated. So that that leads us to an even bigger problem, and now we need an even higher precision solution, or op-amp comparator, or whatever it is that we're doing here, okay? If we choose all these four resistors R1 and R2 to be equal, then we have an attenuation factor of 2, so basically this will halve the voltages, and this will mean an amplification factor of 2 for these errors. So now all of a sudden at 10 amps we will have a 2% error, at 1 amp we will have a 20% error for the voltage that gets generated here on the low side, okay, which is the one that we care. And we will get at 100% error at only 2 amps. So yeah, not very nice, not very nice, okay. Of course, I'm not saying that this is not a solution at all. I'm just saying we need to be aware of the problems that we need to face, okay. So now that we've talked about the high side shunt resistor, now let's see what options do we have for the low side shunt resistor. Like I said, theoretically, the low side sensing is easier because it generates a voltage that is referenced to the ground by default. However, now we need to determine whether we want to power our comparator or op-amp from before the shunt resistor or after the shunt resistor. And here's where things get a bit tricky. So if we measure, if we power the op-amp from the, okay, so let's start with the beginning. Most of the times we will want a shunt resistor that is relatively small as possible, so that the voltage drop on him will not be that big of a deal, okay, in order to have as much voltage on the load herself. Especially if we have tight headroom. If we let's say that we want to have a circuit like I wanted to, that is powered by 5 volts and is able to charge lithium accumulators that, as we know, can go up to 4.2 volts, at least lithium-ion, lithium polymer, 4.2 volts maximum typical voltage. This leaves us only a 0.8 volts voltage drop for the rest of the circuit, for the shunt resistor and for the regulating device, which in my case was a MOSFET transistor, but I will show you details in the next video. 0.8 volts means that, and I want to push up to 10 amps or as close as possible to 10 amps if needed. Well, that's going to be a problem because if I have a shunt resistor of 100 milliohms, let's say, at 10 amps I will have a 1 volt voltage drop, and this is too much for me. And 100 milliohms is not a high value resistor, shunt resistor, but in this case it is. So 1 volt voltage drop is too much, because then I get only 4 volts on the output, or even less, because of course I have a voltage drop on this transistor as well. So I won't be able to charge with 10 amps whatever accumulator I have. So I need to have as small voltage drop as possible. On top of that, this solution is problematic because, I mean, from the measuring current measuring point of view, it's very simple. We simply have an op-amp in non-inverting configuration that takes the voltage on the shunt resistor and amplifies that with a certain factor and gets us a higher voltage that we can easily work with. However, the rest of the control circuitry, especially if the rest of the control circuitry is powered from the same point here, which in most cases we will have it like this, because we will want to use a single integrated circuit with let's say 4 op-amps or 4 comparators or something like that. Well then, the rest of the control circuitry will not be able to regulate the output voltage alone, because whatever voltage he will measure, it will be in the voltage on the load in series with the shunt resistor voltage. So on the load we will constantly have a voltage drop that represents this shunt resistor voltage drop. Okay, so if we set, let's say we set we have a shunt resistor of 100 milliohms, and we have we set the control circuitry to give 4 volts on the output. Okay, if the load draws 1 amp, then we will have 3.9 volts on the output. We will no longer have 4 volts in spite of the control circuitry regulating for 4 volts. If we have 10 amps through our load, then the voltage will drop at 3 volts on the load, because the rest of 1 volt will be on the shunt resistor, and the control circuitry will not be able to distinguish between them. Okay, so this is while this method, you know, provides a clear advantage of just having a positive voltage depending on the current, and no matter how small that is, we can just amplify her with an op-amp. This method also introduces this problem with the voltage drop on the load. Now, this is still an option to be taken into consideration if we decide to use for the current measurement maximum precision integrated circuits, like something, let's say MCP 6V51 or 6V whatever from microchip. This is a so-called zero drift op-amp. It's a high DC precision, has 15 microvolts maximum offset voltage and plus minus 2.4 microvolts typical. And even on the first page of their data sheet, they recommend that we use this this chip for current measurement on the low side with a shunt resistor of, it happens to be 50 milliohms, just like in my case. However, because of this super high precision op-amp, we are able to have very high amplification factors. Like they say that we can have up to 200, an amplification factor of 201, well, in this case, but that one doesn't matter anymore, so let's say 200. In this example that they give us, we will basically get a 10 volt output for every amp that flows through our shunt resistor. Now, 10 volt, I consider 10 volts to be a bit too much. However, this is besides the point. The point is we can go as low as, let's say, 5 milliohm shunt resistor, and we will still have a 1 volt per amp with pretty good precision. Okay, pretty good accuracy. And 5 milliohm resistor introduces only a 5 millivolt voltage drop at 1 amp, a 50 millivolt voltage drop at 10 amps, so it's basically negligible. So we can definitely use this option if we can have the shunt resistor so small that the voltage drop on the load will just not matter, will just be negligible. Okay, but if for some reason we want to use very cheap, easily available op-amps or comparators that are far from being that precise, then this option tends to become problematic. So we have yet another option. While keeping the shunt resistor on the low side, we have yet another option, which is to take these power pins and move them after the shunt resistor. Okay, like here. Now the ground is no longer the minus of the source, but it's this other point after the shunt resistor. This makes it so that if we use the same chip for the rest of the control circuitry, which I drew here as an extra op-amp connected to, you know, this NPN transistor. This wants to symbolize the rest of the control circuitry. Well, this can monitor the voltage only on the load and can regulate the voltage only on the load, irrespective of the current, and therefore this voltage on the shunt resistor. However, now we have we have a different problem that we need to take care of. And that is the fact that we cannot simply use you know, a non-inverting op-amp to have a higher voltage relative to the ground for our current, because that just won't work. If we make the ground here in this point, then every any voltage that is generated on the shunt resistor will be negative to the ground, relative to the ground, okay? And since we're powering the op-amp from after the shunt resistor, we will just not be able to work with any of these voltages at all, because, you know, this op-amp would try to amplify a negative voltage and generate an even more negative voltage, which will be impossible. So this option is not really possible like so. However, it's still a good idea and can be used, but with a bit of a twist. And now we're getting into the second part of this video, where I show you the circuit that I've tested, I've developed, I've tested, and this circuit has been inspired by a particular integrated circuit that is used for, you know, voltage and current control, created by Diodes Incorporated, model APE 4306. At first, when I have taken a look at this, I wasn't really understanding, you know, why this works and how this works, because they have this particular topology with the ground of the control chip placed after the shunt resistor. But after a while, I understood why this works, how this works, and I was able to just adapt this topology for my needs. So this chip, just to quickly mention what this chip has, this chip is essentially similar to comparators like LM339, okay, or 393, because they are electrically identical, which are open collector, very simple, very cheap comparators that we can find in the thousands on the market. They have placed two of these comparators inside the chip. They have connected both outputs, so both collectors together. And they have also placed a voltage reference and a voltage divider inside. The first comparator sees the entire voltage reference of 1.2 volts. The second comparator sees only about 100 millivolts approximately. It depends on the model. There are actually three models, A, B, and C. Each of them have slightly different voltages for the second comparator, but anyway, that's besides the point. The point is, we have the situation of the ground being placed after the shunt resistor, therefore all the voltages on the shunt resistor will be negative to this ground, and yet the circuit works. Well, it's very simple. It works because on the inputs of the op-amps, we will always have positive voltages no matter what, because we are having this voltage reference that is positive, okay? And no matter how much the shunt resistor drops down to the negative, of course there is a limit, but up until that limit all the voltages on the current sensing op-amp will be positive, and only at some point the voltage on the non-inverting input will become zero and the op-amp will flip and will do his thing. So now let's take a look at the circuit that I've derived from this data sheet, and that I've made to essentially work for us, and it solves both problems with the output voltage being able to be adjusted independently of the current, as well as the current being measured on the low side, as well as when I will show you the actual schematics, we will see how to compensate for the input offset voltage in order to get a higher precision circuit out of you know, very cheap, very low precision comparator. So the idea is that we need to create a positive voltage that will be monitored by the inverting input of the comparator. The non-inverting input will constantly monitor the ground, okay? So we'll be tied directly to the ground being the output of the shunt resistor, and this is the ground because we have tied the power supply pins of the comparator, you know, after this shunt. So the non-inverting input will constantly be tied to the ground and will monitor the other voltage on the inverting input relative to this ground. On the high side, we have a transistor that by default gets turned on and normally would stay turned on because we have a resistor from his base to the positive rail, which turns him on again by default. And this transistor generates a current through two different resistors, Ru2 and Ru1 here. Ru1 is connected to the ground and to the inverting input of the comparator, and Ru2 will be the resistor that will generate the voltage that we will care in the end. Okay, so the idea is that as some current is being drawn by the load, and the shunt resistor will develop more and more negative voltage. Okay, this will essentially turn on this. It will make it so that the inverting input will become more and more negative, which will allow this comparator to have his output go up. This transistor will be able to open and will generate a higher voltage here, a higher current, and therefore a higher voltage across these resistors. When the voltage across Ru1 resistor will be the same as the voltage across the shunt resistor, okay, the comparator will keep turning on and off in order to turn on and off this transistor in order to keep this voltage constant. So the shunt resistor voltage will be mirrored on the Ru1 resistor, just like in the example that I've given you here, except the mirroring occurs slightly differently. Okay, so because this mirroring occurs, again we have a current that is literally the voltage on the shunt resistor divided by Ru1, and the same current will flow through Ru2 and therefore will generate a voltage across Ru2. But because this point has right now become a virtual ground, okay, because the op-amp will make it so that this point will become a virtual ground, so we'll have the same potential as the real ground, then whatever voltage we have on resistor 2 will be dependent on the current that flows through the entire circuit, but also referenced to the ground. So we can just take this voltage and feed that to the rest of the control circuitry. And of course, we also have the option of amplifying this voltage, because now if Ru2 is bigger than Ru1, of course, we will have a higher voltage. So essentially, the ratio between Ru2 and Ru1 will dictate the amplification factor of the shunt resistor's voltage, and yeah, it will allow us to have a higher voltage that we can more easily work with. Okay, so just to quickly recapitulate the advantages, we have the ground point that is common with the load, the ground point of this circuit. It's not the same as the ground of the source, but because the ground point of the control circuitry will be the same as the ground point of the load, the voltage adjustment will be done independently of the current. The current dependent voltage will be relative to the ground, which is nice because that's what we need. The current dependent voltage will basically be the shunt voltage amplified by a factor of Ru2 divided by Ru1. Like I said, this ratio gives the amplification factor. We can use simple and cheap amplifiers or comparators like LM339 or 393, which is nice, which is what we want to achieve. And therefore, the rest of the control circuitry can be done with the same model of comparators. And this is an advantage because LM339 has 4 comparators on the chip. And for the rest of the circuitry, we typically only need just 2 more comparators, and that's it. So we can use a single chip to do everything, okay? Now, this circuit is still plagued by input offset voltage. It's just the way the nature of the circuit is. However, we can perform some simple adjustments. We can just add 2 more resistors, and I'll show you in a moment, to get a decent or even good precision. So we can compensate for this offset voltage relatively easily, I would say, and get pretty good precision current to voltage conversions, okay? Now, this cannot be used for multiple voltages with common ground as far as the source is concerned. As far as the load is concerned, well, we can have multiple loads with the same ground, but the sources need to be completely isolated from each other, completely separated, okay? So this is the only disadvantage that we have. But if we have a single voltage, we don't care about, you know, whether we don't have multiple grounds anyway. We don't have multiple points of ground, so because we don't have multiple loads that are independent, so we don't care about this anyway. So now let me show you in more details how the final circuit looks like, because we need to do a few more tricks. So 2 more things we need in order to make this work. One is the frequency compensation. These comparators, these very simple open collector comparators, do not have frequency compensation, and because of that we will have major problems, because they will not operate steadily. They will tend to oscillate. So for that, I have determined experimentally that I needed to place a capacitor here between the output of the op-amp and the inverting input, but not directly the inverting input, rather through a resistor. These 2 resistors are used to perform the input offset voltage correction, and I will get to them in a moment. So I have experimented with multiple capacitors, and I have chosen the smallest value that does the job well enough. And I've determined that experimentally to be 3.3 nanofarads, okay? At 3.3 nanofarads, the circuit is pretty stable. However, the voltage generated was still a bit fluctuating, a bit, I wouldn't say oscillating, but had a bit too much ripple for my taste. So I added, in order to smooth that voltage, I added an extra 100 nanofarads capacitor between the output ground and this output voltage, and that solved the problem. After that, I had a nice smooth output voltage that is dependent on the current that flows through the load, through the entire circuit. So that was pretty much it in terms of the frequency compensation. Now, in order to compensate for the input offset voltage, I have actually used a trick. I have used another error, which is, let me get back. Here, the input offset current and input bias current, okay? So these exist in every op-amp. What remains to determine for each op-amp is whether or not these are currents that flow out of the inputs or into the inputs. For these particular models, these currents always flow out of the inputs, from the op-amp out of the inputs into the rest of the circuitry, okay? So we will constantly have, let me make a print screen and make some drawings to better show you. So here we will always have voltages like so, okay, that have the plus here and the minus here, because currents, the input bias currents always flow from the op-amp out of them through the input pins. Why is it so? Very simple, because if we go back to the internal circuitry, okay, so if we go back to the internal circuitry of these op-amps, of these comparators, we see that we have PNP transistors, okay, and we even have the arrow of the emitter showing us the direction of the current. So we have here an 80 microamp current regulator, okay, which pushes the current down here, and this current will split into two different branches, one for each input, and a very small portion of this current will eventually go through the emitter base junction and flow outside through the input pins, okay? And this op-amp will never have currents in reverse direction. So if on the input pins we place resistors relative to another point, let's say ground, then we will always have a positive voltage here. And based on whatever, these currents are constant, okay, because this is a constant current source. Therefore, by placing a fixed value resistor, we will always have a constant voltage across this resistor. And this is the trick that I use to compensate for this input offset voltage, okay, for these a few millivolts of input offset voltage. I'm using these tens or hundreds of nanoamps of bias current in order to generate the voltage that I need in order to bring the two inputs much closer to each other. So I started by using a single, so on a breadboard, and this is another important aspect that you need to understand. There might be a difference between what you do on the breadboard versus what you do on the actual board if you decide to solder the chip himself directly on the board, which I do not recommend. I recommend that you use a socket, and you solder first the socket on the board and you place the chip last at the very end. Why? Because by applying heat to the chip, the internal structure of the semiconductor will change a little bit, which will essentially modify these currents and these offset voltages. And if you have tested this first on breadboard, then when you will create the circuit, you will see that you no longer have that precision that you've established on the breadboard. So in my case, I did not need it at all, this R13 resistor here. I could just connect the non-inverting input directly to the ground, and I have determined that I need a 3.3 kilo ohm resistor here on the inverting input, and that was about it. However, then I proceeded to soldering the chip on the board, which was a bad idea, and this introduced another imbalance, which I needed to correct through this R13 resistor. Not a big deal, but I'm just saying this is something that you need to understand will happen. The idea is that based on whether you have more voltage on the minus input rather than the input or the plus input, or the vice versa, you will need to add one resistor or another, or sometimes just even both. Honestly, I just recommend that initially you put you don't put R13, you just connect or you place a jumper instead of R13. You place this resistor R14 here, 3.3 kilo ohm, and then you perform some tests and you see how well the circuit goes. The idea is as follows. If on the output, and I remind you that this is the output, okay, this point here, if on the output we have more than 0 millivolts at 0 current, then we need to increase this resistance on the minus input. However, if on the output we have some negative values for currents between 0 and some value, then we need to increase the R plus resistance, which is R13 here. And I will show you in a moment what I mean by that. Now, just to clarify a bit what I wanted here, I wanted to measure currents from 0 to 10 amps with a maximum voltage drop of 0.5 volt. This means that I placed two shunt resistors in parallel, 100 milliohm each, because I didn't have smaller shunt resistors. So placing two in parallel will give me 50 milliohms, which at 10 amps will give me 500 millivolts. And this is the maximum voltage that I accept. Okay. I also wanted this circuit to give me 1 volt full scale range. So for 10 amps I wanted to have a 1 volt, which means that I needed to amplify this shunt resistor voltage by a factor of 2, only 2. Okay, so I placed a 100 ohm resistor here on the bottom, and I would have needed to place a 200 ohm resistor here on the top, but of course 200 is not a standardized value. I placed a 220, and I accepted that, you know, my values can be a bit higher. As it so happens, because these were not precision resistors, the ratio between them ended up being 2, exactly 2, and I will show you in a moment when I will showcase the functioning of this circuit. Okay. Yeah, and that's pretty much it in terms of what values we need to choose and how. This 15 kilo ohm resistor, can be a bit higher theoretically, can be a bit lower, especially if we use low voltages. Like I chose a 5 volt power supply, because this is what worked best for whatever I needed in the rest of the circuit. Again, I will present to you that in the next video. So let me show you how well this works, how well I was able to, adjust everything, and let me explain to you a little bit more about this input offset voltage compensation. Okay, so what we have here is the circuit. Well, it's a bit more than the circuit, but on that board, at least half of the components are for the circuit that I've just shown you. On the right, we have a yellow multimeter measuring current through the load, and I had an adjustable electronic load. And on the left, we have a multimeter set to measure millivolts for the output of this entire circuit. The idea is that for every amp on the right, we need to have 100 millivolts on the left, or as close as possible as 100 millivolt on the left. And this is more or less what we will see. So at some point I started drawing some currents. Okay, at 60 milliamps, we have 2 millivolts. At very small currents, precision is not all that great, but it's not that big of a deal. It's not that big of a problem. After all, we are using a very cheap and very not precise, comparator. Also, I could have performed the adjustments a little bit better, but I decided to just leave them as they are here, because they are pretty good. Okay, so 600 milliamps, I have 51 millivolts, so it's only 10 millivolts off. Then I was drawing 1 amp, and I had 93 millivolts, which means 0.93 amps. Good enough. Then I started drawing more. Besides that, I was also monitoring the ripple on this voltage, just to see, how bad or how well this ripple is. And we see here we have 1 millivolt per vertical division, and the oscilloscope was made to capture in average mode, so that, I would filter out the noise from this ripple, and I get about 1 millivolt peak to peak of noise, of ripple voltage, which is pretty good. 1 millivolt out of almost 100 millivolts, that's pretty good. So I have a pretty stable output voltage. Okay, at 2 amps, okay, we see 1.92 measured. I was checking the ripple again. Ripple was somewhere between 1 and 2 millivolts. Still good. 2 millivolts relative to 200 millivolts, pretty good. Okay, and then I kept going up with the current. 3 amps. Okay, 3 amps is, let me get 2.9 measured from this simple circuit. And the ripple went up at around 2 millivolts or so. Somewhere between 2 and 3 millivolts. Again, pretty good for, you know, simple circuit like that. 4 amps, 3.9. So I'm off by 0.1 amps constantly. But again, this can be resolved by performing an even better offset correction. I was happy with my results. This is why I left them there as they are here. Here the ripple is about 4 millivolts, which is again pretty good. 4 out of 400 is essentially 1%. Then I went up at 5 amps, and at higher currents I tend to be on par with the actual measured value. Okay, 6 amps. And I was able to go up to 7 only with my load. My load could not draw more than 7 amps, but I do not care about it. It's pretty clear that this will work at higher amps as well, and 10 amps is the maximum that I designed this anyway. And the important thing is that at 0 volts, you know, we have at 0 amps, sorry, of current, we have 0 millivolts. This is important because when we want to sense smaller currents as well as bigger ones, we don't want to have a situation when the output of such a measurement circuit remains at some offset voltage at some, I don't know, 10, 20, 50 millivolts, even when the current is 0. Okay, this is something that we want to achieve. Just 0 millivolts for 0 amps of current. And the compensation was pretty good in this regard. Now, let me show you what I meant when I said that, you know, sometimes you may have output negative values for currents between 0 and some value. And then we basically need to increase Re13 here, the resistance in the plus input, in the non-inverting input. So here we had a situation when I was increasing the current, okay, the current that I was drawing, and the output of this measurement circuit started to become negative. Why was that? Well, that was because this comparator insisted on keeping the transistor shut down, and therefore the voltage on the output was none other than the voltage across the shunt resistor, which was going negative, more and more negative, as I was drawing more and more current. Okay, this is because the comparator was not seeing correct voltages due to the offset, the input offset voltage, and was allowing for this phenomenon to happen. And at about half an amp of current or so, the comparator was able to function completely, so that the output was again 0 volts, but everything from there on was shifted by basically half an amp of by 50 millivolts, which is half an amp in our case, and this represents an error. Okay, this is why we need to let me play that back again. Okay, so when we have this situation, okay, this is when we need to increase Re13 up until when we have no current whatsoever. We need to have 0 amps, and as we start drawing even small currents, we need to have a few millivolts on the output. Okay, and this is how basically you need to try multiple value resistors until you get the right one. In my case, the right one was around 100-120k. I would have gotten an even better precision if I would have increased this from 100 to, let's say, 110 or 120 or so, but I chose to leave it at 100k. It helps if you have a resistor decade box, okay, and you just place 2 wires, connect them to the decade box, and then just manually adjust until you get the right value, and then you know exactly what resistor to place inside of here. Okay, so yeah, this is pretty much what you need to do in order to achieve a pretty good precision current monitoring circuit that has low voltage drop and can allow you to measure even a 1,000th part of the maximum current. So I can measure up to 10 amps and down to just a few tens of millivolts, like 30-40 millivolts. Okay, that's a pretty wide range of currents. So thank you very much for watching. I hope you learned something useful. I will show you in my next video where exactly I needed to use the circuit and how can we create a very simple accumulator charger that allows us to use an old computer power supply and allows us to push quite a few amps of current into the charging of that circuit, of that accumulator, while at the same time we will keep the power dissipation pretty low. So thanks a lot for watching. Many thanks to the sponsors and supporters of this project. If you would like to support me for free, a like and a subscribe to my channel doesn't cost you anything, but allows the YouTube algorithm to, promote my videos to other people who may be interested. If you would like to support my work financially, you can find a link in the description to my Patreon page. I show my appreciation to all my supporters. So thanks a lot, and I will see you soon in my next video. Bye bye.